Today is actually a break with a complete break with the material that we've been looking at before, because all of the methods that we've talked about so far we've referred to as domain type methods. And in other words, what we do is you fill up the volume of your solution space. If it's 2D, it'll be a 2D matrix of elements, triangles or quadrilaterals that fill it. You apply boundary conditions to it, and then from those boundary conditions you solve for both the unknown boundary conditions around the edge. So if it's a flow problem, you prescribe a portion of the boundary which is pressure defined, and you'd solve for that part, you'd solve for the velocity. And likewise for the part that is flow rate defined, you solve for the complementary condition. And then you solve for the interior conditions as well, pressures and flow rates, flow velocities in the interior. And so that is the solution methods that we've talked about so far. And so we've used this. Actually, you might draw it. It's a bit blunt. It's a bit of a blunt instrument, that one. So we've. I don't know. So the geometry that we had drawn before was something that might be a tunnel below the surface, bless you. And what we did was he said that we would divide this up into a series of elements. And I'm going to get bored about filling this up, but you know exactly what the deal is. And these elements allow us to solve for the appropriate conditions, both on the boundary, which might be here and here, but also in the interior. So these are domain methods, which we've called them. And we can also talk about boundary solution methods, which are fundamentally different. Say different, I was going to write methods, not different. And so here, if we wanted to solve this problem, maybe if it had a free surface, or maybe this was the free surface where the water table was, and we had a tunnel or a drain below that, then the meshing for this element would actually only be on the boundary that mattered. And so the boundary that mattered would be the boundary of this individual tunnel, which we would discretize. If we had a free surface here, then we'd actually have to discretize this as well. And we'd probably have, if we had some kind of fake boundary that we had to consider, then we'd have to put elements on here. But you notice that for a two-dimensional problem, the elements that we have are two-dimensional. But for boundary solution methods, the elements that we have are really only one-dimensional, just line elements. If this, for instance, was a tunnel, maybe in an infinite medium, then actually the solution that we would discretize would actually just be this. It would only be on the boundary. It would still be these one-dimensional elements, but it would actually automatically account for the fact that the domain goes to basically infinity. Obviously not infinity, because the planet's a sphere that's floating around in the universe, but it's not infinite itself. But for our intents and purposes, it's very large compared to this domain, and we could consider it infinite. So these methods are often used in problems, geological problems, because they typically have a very large volume to surface area ratio. And so the surface area is relatively large, but you're solving in a very big volume, and so you can do it quite efficiently for geological problems, as opposed to a gidget, which might be, I don't know what it would be. It might be a tent peg or something. I'm not really sure what it could be. It could be any gidget you want to think about it. The volume of this is relatively small compared to the surface area, if this was a tent peg that you bang into the ground, or a knife or whatever. And so for geological problems, boundary solution methods are actually quite attractive. As with everything, they have positives and negatives. The domain methods have the drawback that you have to mesh throughout the body, and that may make a lot of nodes and elements, and that may make you a very large matrix. But because you mesh throughout the body, you could conceivably have a different permeability in each element, which may be accepting heterogeneity, which is a realistic, is a reality in these systems. Or it could be that the heterogeneity is something that develops. So in other words, it could be a permeability that changes as a function of saturation. If saturation changes and the relative permeability changes, then you can do that quite easily if you have these systems. So boundary solution methods, they tend to be really great for small surface area to volume problems, so small surface area versus large volume, geological problems. And they tend also to be limited to linear problems. So linear problems both where the permeability may be constant throughout here, not layered and not changing from space to space, and also where that permeability isn't changing as a function of, say, saturation that's changing within here, or as a function of pressure gradient. And so they're typically very good for solving linear problems and not so good for solving materially nonlinear problems. So like our subdivision of other methods before, we talked about boundary element methods. And so all the things we'll talk about today are boundary element methods. But they're also classifiable in certain subdivisions. Certainly boundary solution methods or boundary element methods can solve the flow problems that we talked about for fluid flow and heat flow. They can certainly solve the solid mechanics problems, and they can solve both static and I guess we'd call this elastodynamic problems, so wave propagation problems. I was just going to write my name almost. Who the hell is this guy? For wave propagation. They don't solve, so for wave propagation and transient problems, certainly steady state problems are very easy to do. And I suppose that might be worthwhile mentioning that these are steady problems are easiest to do. Because if you start doing transient problems, or if you start doing problems such as advective transport, then all of a sudden you actually have to distribute elements within this domain. And so, to me, you lose many of the advantages of this in being able to get away with a really easy mesh. And so if you're thinking about things like hydraulic fracturing, for instance, you have a borehole and you want to have a fracture that comes out of here, then it's very easy to remesh this fracture as it grows. And that's why these problems are also used for solving fault problems. So you have a fault that has some slip on it because you have stresses acting on it. And you can look at the strength criterion along this fault. You actually only have to represent the fault on its own, and the infinite media outside it takes care of itself. And so that's, again, kind of the advantages of boundary element methods. These boundary element methods array themselves into two types, and they are referred to as either indirect methods or direct methods, and for all of these kind of solution types. And again, we'll talk primarily, we'll talk about both, but we'll solve a little problem using indirect methods primarily. And the idea for indirect methods is that you set up a system of equations and you define some influence functions. And so in our particular case, it could be that if we're looking at flow problems, we've defined this matrix that we know can define flow rates as a function of some matrix and heads or pressures defined at the boundaries. So we know what the relationship is between these two components. We know that we have to do it with kind of a mesh of elements, but we're not talking about that here. So what we're talking about here is setting up a system where we could, for instance, how are we going to best do this? Let me illustrate it actually with the example that we'll talk about. And so we'll solve a little problem which is basically a bit of a contrived problem, but I think it will illustrate exactly how the method works perfectly. And we'll solve a problem actually not dissimilar from the one that we've solved before for flow, and that is flow within a block that's constrained top and bottom with no flow. And so what we could do is the indirect method basically allows us to be able to figure out exactly what, if we had a source at this particular point on this thing, and we could calculate what the influence of that source was on this other side, and actually on all of these individual components. What we could do is we could array a what we could do is we could array a distribution of these sources on these four faces. And by a source for the flow problem, I just mean that it's flowing, it's sucking water into this little slit from both sides. Just imagine we could cut this and we could make a little slit and we could suck fluid from the porous medium that exists to infinity on every side, and we could figure out exactly what the impact of that removal of fluid was, say on the pressure or head at each of these other locations. And so the indirect method is called indirect because it figures out exactly what the strength of this source would have to be at each of these points so that it directly matches the boundary conditions that we have at each of these four locations as well. So that's the essence of the problem. So it's indirect because you do two things. You solve indirectly. First of all, you figure out exactly what the strength of these sources might be that would give you the right boundary conditions at these points. And then once you've done that, you use the strengths of these sources to figure out what the behavior is on these boundaries for the complementary boundary conditions, right? So on this boundary, we're saying that the flow velocity is 0. And so that's something we know. So if you look at this, we know that the head on this boundary is equal to 1, say. I think that's what we're going to use. We're going to have the head on this boundary as equal to 0. No flow boundaries top and bottom. And so we're going to figure out exactly what the four values of Q would be that would give us these boundary conditions. So that's told us what the values of Q would be, but nothing else. So then what we can do is we could apply these sources and figure out what, as a function of these four sources, the strengths of these, would be the complementary condition at each of these points. And so here we know that the flow rate is 0, but we don't know what the head is. So we calculate the head from the complementary condition. Here we know that the head is equal to 1, but we don't know what the flow rate is, so we'd solve this. So this is the one that we'll do a little example with, which is why I say this is, for me, this is an interesting class, because it takes a topic that's relatively complex, and I think it exposes it to be somewhat more straightforward. So these indirect methods are sometimes referred to as fictitious source methods for flow problems. So this is for flow. And for solid mechanics problems, they have two distinct terms. Some are called fictitious force methods, following on from this. And some are would be called, just to keep it common with this terminology, fictitious displacement. Sometimes actually referred to as displacement discontinuity methods. methods, or DD. And so, in the same way that we talked about, if you could call this uppercase Q if you wanted to, but for the solid mechanics problem, each of these have been defined as basically we solve F equals KU. You could imagine this being defined on an individual element, or you could imagine maybe an element which was this kind of super element that is the whole geometry of the system you have. We've always thought of elements as being individual triangles or something, but what if, for instance, the element was this whole geometric body? And so the idea is that what we could do is we could apply a force in an infinite medium. So in other words, we could take a force and we could apply that force at a point, and that force would give us a induced force at some other location and also an induced displacement. And so what we could do is we could write a linkage between these forces and displacements around this body. And if we choose the magnitude of the forces that we distribute around this body to recreate the boundary conditions we want, then we have a solution because it's satisfying all the requirements for a solution. It's satisfying the equilibrium equations, it's satisfying the constitutive equations, Hooke's law. And so now when we apply those forces, we could use it to determine the complementary boundary conditions. So if we applied fictitious forces, we could figure out what the complementary conditions were the displacements of those locations. Or if we applied a unit displacement at a location, then we could calculate again what the forces and displacements are somewhere else, and we could solve for, again, the complementary conditions. So that's maybe a bit complex. And so the fundamental solutions for these, for the displacement discontinuity method, is basically a crack. So it's a small crack, a bit like this idea of a slit source, and the crack it can open in opening, or it can deform in shear, I guess US. And so what you could imagine for this is if you put these cracks around your geometry, just like this, if this was, for instance, the board duster, which I don't have behind me, and you could solve for the normal, I guess I should call it UN, and the shear displacements on each of these four elements so that you satisfy the boundary conditions, then you can resubstitute those source strengths in to be able to figure out exactly what the complementary conditions would be. And so we'll do an example. We've spent too long talking about this already to do that. Direct methods are called direct because you solve directly. So for those, again, you have a geometry, but you set up a system of equations which would give you, for the flow problem, it would give you something like a vector, a matrix of known terms multiplied by flow velocities, Q, and a vector, a matrix of known terms multiplied by the boundary conditions, V. You know every single component in these H and Q matrices because they're just geometric relationships, and it allows you to solve then for the appropriate boundary conditions on that. And so these are sometimes referred to as boundary integral equation methods. Oops. Equation methods. Sometimes by the acronym BIEM, not surprisingly. So, and we'll talk a bit about those if we get that far, and we probably will actually. So two basic classifications: indirect and direct. Indirect because you solve indirectly for the unknown boundary condition by going through this intermediate part where you get the source strengths and you then apply those source strengths in a second iteration to give you the complementary conditions. And direct methods because you just solve in one step. You can put these two matrices together absolutely, you'll know half of these boundary conditions, half of these boundary conditions, and you have a set that you can then solve for. So that's it. So those are, as we mentioned before, indirect methods are by far the most intuitive, I would say, and so that's why we'll concentrate on those. We can apply them to groundwater flow and elasticity problems. Again, groundwater problems are going to be simpler because we're dealing with a scalar rather than a vectoral quantity. And so that's the one that we'll choose. So we'll do exactly this. And if we have time, we'll talk about direct methods again applied to the two systems. And the other thing that we could also chat about if we have time is that you could think about using these methods in their combined strength. So in other words, if domain methods are really great, finite element methods are really great for places where permeabilities or moduli vary with location or as a function of the stresses or strains or the fluid pressures or saturations, for instance. In other words, they're nonlinear because of one of the dependent variables. Then presumably what we could do is we could use a domain that has finite elements on the inside and then grades on the outside to take it to infinity with boundary element methods on the outside. And so that way we'd be able to get the benefits of this nonlinear response on the interior where it works at its best, but also be able to represent this medium that goes to infinity and beyond, outside that, by this somewhat more effective method where it's essentially linear outside. And so you could think about combining the two methods to be able to do that. So that's the deal. So let's move away from the arm waving and then talk about how we'd implement this in terms of the direct methods. So for flow problems, this is the idea. So imagine that you can drill a little hole in an infinite porous medium that goes forever. The drilled hole goes an infinite direction in the z direction in this particular case for this coordinate system. And you pump fluid into this little hole so that it goes into the porous medium that's around it. If we did that, it's just like a well. You could imagine going some distance away from this well, which would be some distance x and y. And we could calculate from a solution for this just by solving the continuity equation and using Darcy's law. We could get the head at any point as a function of the strength of the source, which is, you could work out what the units are for this. It has to be units of length, I guess, in this case, because this is a head. So the source of the strength, you double the strength of the source, you double the perturbation in terms of the head. You quadruple it at the same point. And so what we can do is we can define the magnitude of the head at a particular location. We could also calculate, if we know that the velocity in the x direction is just equal to hydraulic conductivity dH dx, if we differentiated this, then we could calculate what the velocity was in the x and y direction. And that's all this term is. And you could do that yourself. So coming back to our desire, we want to be able to have some perturbation. And these are called kernels functions, or sometimes called Green's functions. And what they are, they're fundamental solutions for a point source in an infinite porous medium, or a line source actually in this case, or a point force or a point displacement in an infinite medium. And so what we have are the velocities that result from this. What we could then do is we could take this source, and instead of just applying it at a point, we could apply it at a whole bunch of different points along the x-axis over some length. And so this is getting close to being able to represent our little slit of an injection source, which we can use on our boundary. So that's exactly what this is. This is our injection source. It's pumping out into the medium. It would be just a value of, this would be, so it would be something like the integral m dx, right? It would just be over some small portion of this length, dx, would be what the integration is. And as a result of that, now what we can do is we can calculate what the velocities would be in the y direction and in the x direction, merely by doing that, just by integrating this particular source between the two limits, between x1 and x2. So we don't have to do that because we have the solution here. So this is the solution from taking this individual point source and distributing it all the way along this segment here. If we do that, then we find that the head at this location here is equal to this expression. This would be the 2 and the 1 just mean it's the integrand, so x1, r1, x1, well, I guess it would be 2, right? x2, r2, x2, y2, theta 2 minus x1, r1, x1, y1, theta 1, right? Just by using this appropriate geometry. And so we can work that out. And so what we'll do is we'll call these terms B. So they're the influence of a point source in defining the head at a particular location. So the complementary behaviors would be calculating what the velocities are at the same point, where we have two components, one in the x direction, one in the y direction, and they would just be by substituting terms into this particular relationship here. So this would be, in sequence, it would be 2, and then it would be 1, and it would be, so it would be log r2 minus log r1, which would be the same as log r2 over r1, etc. So we can calculate these components. So remember that these are for the solutions for an infinite medium. So there are no boundaries in this whatsoever. And so what we'd like to be able to do is, if we are representing the geometry that we talked about before, that we said would be a no-flow boundary here, and a no-flow boundary here, and a head equals 1 here, and a head equals 0 here. Clearly this is not an infinite medium, right? It's finite. It's a block that has these particular pressures on it. But what we're going to do is we're going to forget the fact that this is a finite medium. We're just going to think of it as an infinite medium. And we're going to put these sources in this infinite medium, and to try and make sure that when we apply these sources, it replicates these particular boundary conditions that we've defined here. And the boundary conditions are a head prescribed here, a head here, and 0 velocities on these other boundaries. And so this clearly is an infinite medium. This clearly is a finite medium. But so long as we represent these boundaries appropriately, it doesn't care what's going on out here. It just cares what's going to happen inside this and the boundaries that are attached. So what we could do is, in taking this particular geometry, still remembering that it's in an infinite medium, and what we'll do is imagine that we would take a little line source in this infinite medium, and we'd put it here. And this would be flowing both outside from the, would be flowing in both directions away from this little slit. And what we could do is, this is what we're representing here, is we'd like to be able to calculate, for instance, what is the head at this point, what is the velocity at this point. And so we'd draw this little geometry here, where this is the point that we're interested in figuring out exactly what those behaviors are. So this is the idea. So we're in an infinite medium. We're going to define the boundary of this medium here as this, or the unperforated boundary. So pretend this isn't really a boundary, but because the medium is infinite. We have a line source that we put along one side, and we can calculate at every point around the boundary what the influence would be. It's not a boundary, it's unperforated right now. And so in the same way as we talked before, we could calculate what the velocities in the x and the y condition directions would be, right? This would be a velocity in x, because it's parallel to this kind of local geometry here. And this would be the velocity y. But we'd like to change it to be a scalar. So what we could do is we can use the outward component of the velocity at this point, which is a unique value. There's certainly a velocity component in the y direction, there's certainly a velocity component in the x direction, but it'd be nice if we only had one value instead of two, and the only way we can do that is we can take the dot product of this. And so the dot product is just the component that is aligned along the outward normal. And we can calculate that just from the direction cosines of these angles. And so that's it. And so the main thing that hopefully we get from this is that we could write an equation which would allow us to calculate the head at any point as a function of the sum of all of the particular kernel functions being applied on the boundary. So one is here, so that'd be one. Second one would be here. A third one could be here. A fourth one could be here. A fifth one could be here. Sixth one, etc. You get the picture. So in this particular case, I guess we'd have 1, 2, 3, 4, 5, however many you get, 6, 7, and 8. So in other words, we could calculate what the head is at number 5 by taking a source at number 1 and applying it. We'd get one value of this. And so it would look something like this. H5 is equal to the source applied at this location. So B15 times its strength plus B2 on 5 times its strength plus B3 on 5 and its strength all the way through to 8. Times M8. So this is physically saying, it's only saying one simple thing. If we know what the geometric relationships are that give us the influence of this on this particular one, we can calculate all the B values. But all this is saying is that the sum of all the effects of these individual sources on this particular one are the effect of this one on this, plus this one, plus this one, plus this one. This is just using superposition. And so all that's important in this is that we are able to get the magnitudes of these influence functions which define the values of heads as a function of the source strength. We can also get from these previous expressions here the magnitude of the influence functions that give the velocities, which would be these terms, through the dot product, for the reason we said before. And we'd get a similar expression that we could write for each of these, just using A, to calculate now the velocities. So the velocities would be, the velocity at 5 would be equal to B I 5 mi, I guess, right? Sum of. Not B. It would be, get rid of the whole thing. It's going to be A, right? So it would be the velocity at location 5 is going to be the sum of all the influence terms, which are A, just using this term here, I 5 times M I. So I equals 1 to 8. Right? Just exactly this expression. And so that's all we have to remember, that we can get these influence functions. So the reason I said before some of you came in that this is my favorite class to chat about is because we do, I think it's a cool example. So we're going to do this exact problem, this problem here. It's the one that we kind of mused before. No flow on this boundary, no flow on this boundary, an upstream head on the upstream boundary, and a downstream head of 0 on the other boundary. And so you'll notice that we have boundary conditions of two different types. And so I think I've said most of these things, but just maybe just quickly to go through this. So what we're going to do is we're going to distribute sources sequentially on each of these boundaries and find out what their influence is on the centers of these elements. So these will be our boundary elements. This will be one boundary element along this side, a second boundary element, a third, and a fourth. We're going to set up these appropriate equations. We have 4 particular elements. So we're going to want to calculate 4 values of these influence functions, the strengths of the sources that satisfy our boundary conditions. Once we have those boundary conditions, we can write a complementary set of equations. You'll notice now that we want to calculate the velocities. We knew the heads on the boundaries, so we want to calculate the velocities. We'll use the different magnitudes of these Green's functions, but they're linked together by the same values of the source strengths that we had from before. And so that's basically the solution. So we calculate what these source strengths are that satisfy the boundary conditions. So these are BCs. These are sources, which we don't know, the strengths. Once we know what these sources are, because we know all of the boundary conditions, and we know all of these functions here, we can calculate this. Once we know that, we can write a complementary set of equations, which are, if you like, the opposite of this, where we solve for the known source strengths, which are these. We know all of these geometric factors. You see they're switched. And if you like, we solve for the complementary BCs. Complementary BCs. And once we've got the complementary BCs, we have our solution. If we wanted to calculate the magnitudes inside the boundary, we could also do that as well. So this is the deal. So, to recap, we're going to use this terminology that the terms that give us the heads from the source strengths are these B values, and the terms that give us our velocities from our source strengths are the A values. Right? And so we're going to write a system of equations that describe this system. So what we're going to do is we're going to put a source at this location here, and we're going to calculate for element number 1 what is the velocity that we want to apply. The velocity we want to apply, I think, is that this is 0. Normal to the boundary velocity is 0 by this definition. So we know this term here. But what we're going to do, oh yes, I knew it was going to do that. I don't know that it works on this. I think it's a DC voltage on this for the clickers. So let's see if it'll work. I might have to relocate. Oh, it does have enough reach. It just makes it heavy, thanks. I remember plugging it into the DC one before. That one doesn't. Apparently I do. Will it move? You'd think with these.
Do you have the new kind?
Yeah, this new kind. Yeah, thank you. Great. Saved. Okay, come on. Don't you think the greatest invention they make now are the headphones that have flat cords? You have those?
Uh-uh.
Oh, they're great. Little flat.
They don't tingle?
No, they don't. Yeah.
I need them obviously.
Yeah, I think they're a good thing to get. Yeah, you do. You need it on this. I think they're in good shape. Yeah, great. Thank you. So, what we're going to do is to each of these portions, we're going to move a source from one portion to another. And then write the constraint equation. So maybe we look at this. So this is basically the idea. Is if you take the equations that we had, so in other words, the equations are these two equations, this one, and these two to the right of that mark, then what we can do is we can calculate the effect of putting a source at this particular point. So where is it? Whoops. This is it. Yeah. So if you take the source, actually it's a sink, isn't it, in this particular case, because it's coming into it. So this is just showing that there's a flow into it. If you take this uniform source and apply it over this side, which is in an infinite medium, then we can calculate two things. We can calculate the head that's induced by this source at any point within the medium, and we can calculate the flow velocity that results from this. So just using those equations, this is what you end up with. And you can rationalize it. So you're sucking thing into this slit. So you imagine that the velocities would be in the directions of these two arrows, right, into this. We're only calculating it at this particular point. We could calculate it at other points if we wanted to, but we're going to choose to do it in the middle of the elements. And so they're kind of unusual elements for us, right? Our finite elements have always been an element with a little node at each end. What we're doing is we're making an element with a node that's really in the middle where we calculate things. And so if you imagine stuff flowing into this, you'd imagine the big velocity here, into from both sides. You'd imagine that it would be flowing. So if you drew the streamlines for this, right, it would look like this, I think, right? You could imagine it looking like this. And so this and this, I'm going to erase this in a minute. This are the two velocities you have here, and this is kind of exactly what you're seeing at that particular location. And so that's what we're attempting to represent. What else do you see? This happens to be a negative head, doesn't mean anything, but this negative value is smaller than these, which are minus 0.05 versus 0.7. And this is a slightly positive one. So certainly as you go further out, you'd expect this cone of depression is really kind of what you can think of as in terms of the pressures, that these would be higher than these values, which would be higher than this value. These are symmetric to each other, as you'd expect, just because of the symmetry of the problem. And yeah, and this value here is smaller than this. You can imagine because it's just further out. So those are the solutions for the kernel functions that we'll work with. And so what we're going to do is I guess we can do this. So these are just the magnitudes that we have here. So you put a source at location 1, and you calculate the effect at each of these elements in turn, and you can define it in terms of heads and velocities. So how are we going to... So yeah, so the one update since I used this last is that it's changed this. I have this. And the reason I have it in preview is that in preview you can actually do this. Well, apparently you can do that. You can make it a bit smaller, I suppose. You can rotate it. Back where it was. So let's go back to what we're trying to do. And let's try doing this. Yeah, this. So this is the idea. So we want to put together a system of equations that represent this. We numbered this 1, 2, 3, and 4. We said that we want to put together four essential equations. This is going to be no flow here, and a head of 1 here, and a head of 0 here. At the first element, we know that the velocity normal to the boundary is by definition equal to 0. Right? And this has to equal the velocity that's induced by a source at location 1 with a magnitude of source at location 1 on location 1 of m1 plus a source at this location. And I suppose we should figure out what our convention is going to be. So a source at location 2 that influences 1 and is of magnitude 2, and a source at location 3 which is applied at 3, has an influence in 1 and has a strength of M3. And finally a source that's placed on here which is located at location 4, applied on 1, and has a source strength of M4. And so that's our expression that would describe that behavior. We could figure out exactly what these terms are. We don't know, we're not going to know what each of these M values are. That's what we want to figure out. And so what we could do is we could try and use this thing here. Yes, if I can make it just the right size. Let me get rid of this. Let's do a single page. Let's hide it. So this is the idea. So we're first of all going to put this, I can't write on this, that's unfortunately. We're first going to put this element here and find out what its self-influence is onto the magnitude of the velocity. Well, the self-influence, if we drew a normal to the boundary vector here, it would be -5, right? The velocity at this location would be -5. And so a unit source strength would give us a velocity here of -5. And so I think this value here is going to be equal to -5 times m1. Then we're going to take this source and we're going to put it on this, and we want to find out what the magnitude of the velocity it induces in this direction is as a result of this source. And so the magnitude of doing this is source is now here. It's going to have an influence on this point. And so the magnitude of the outward normal here, the velocity in that direction, is equal to 1.28, but it's in the opposite direction. It's flowing. The outward normal is in this direction, pointing upwards. The flow is in this direction, so the magnitude of that velocity is -1.28, just from the geometry. So let me get rid of this. So now we're going to put this element down here. And we're going to, I guess, see if I'm a quick learner. Command L should take it the right way. Yeah. So now we're putting it here. We want to know what the velocity is induced at this point. It's 1.48. Again, it's in the negative direction. And so this would be -1.48 times m3, which we don't know. And then when we do this, the final one, it's going to be 1.28 because it's here, and this is going to be -1.28 times m4. So, and we know this has to equal 0. So that's our first equation. Hopefully it's right. Let's see. Let me just check this. Don't go all the way through it. Yeah. Yes. Where am I? I'm here. Yes. Actually, this is a plus, but so I just take this as a plus. We can explain that away later. So that's one boundary constraint equation. So we have 4 unknowns of these m values. We don't know any of them. But if we want to calculate them, we need 4 equations that would allow us to solve for it. So we go to the second place. We know that the second place is where the head is known. So this is node number 1. This is node number, or element number 2. So the head at 2 is equal to, what did we say? B applied at 1. is affected to times, no, okay, you should have corrected me, right? A, right? A 1, 2 times M1 plus A at 2, 2 M2 plus A at 2, 3 M3 plus A at 2, 4 M4, just by going from this thing. So in other words, again, we're going to put a source here, but now this boundary condition is defined in terms of a head. This head is equal to 1, which we know. And so now when we apply these little sources, we want to know what the effects of these sources are on the heads at each of these at this location. So we can apply it here first. And if we do that, we end up with this. This is L. So the source applied here, it gives us a head of minus 0.0, sorry, so it gives us a head of minus, yes, gives us a head of minus 0.05 at this point. So this would be H2, which we know is equal to 1, is going to be, what did I say, 0.05? Minus. We're going to put it now on itself here and find its self-influence. So this would be minus 0.27 times M2. We would put it now on this third location and see what the influence of this on here would be. And that would be plus 0.0062 times M3, 2 o'clock already. And then the final one is we put it here, and its influence is minus 0.05 times M4. And so we are going to know that this is equal to 1. Again, we know all these coefficients, but we don't know exactly what these are. And so for number 3, we would get the third equation. The velocity on this boundary is defined, so it would be v dot n at location 3 is equal to the sum of the b values. Ij, mj. And for this one, we'd have a fourth constrained equation, which be the heads at location 4, which by the way are equal to 0, which are equal to the sum of, did I do it the wrong? Yeah, I think that's right. Ij times mj. And so now we have 4 equations and 4 unknowns. And so if you look here, where is it on this equation? So these are the equations that we have. We've populated these just to write it out in a way that we can see it. We have 4 values of these m terms. We know all of the boundary conditions, and I think we know all the values of the components that should make up the matrix. And if we've done it right, we can put together a matrix, which I suppose can look like this. So the matrix would be this. It would be v dot n1, h2, v dot n2, and 3, and h4. It would be equal to a 4 by 4 matrix, which is the population of terms that we have here, times m1, m2, m3, and M4 that we don't know yet. And we'd be interested in putting into these relationships that we have above it on this page. And it would be, I'm just going to change color to make it more apparent, it would be this. So I think it's 5. It is minus 1.28. It is minus 1.48. And it's minus 1.28. This one, the second equation is written in terms of a head, so it's these values, minus 0.05, minus 0.27, minus 0.0, sorry, plus 0.0062, this term here, these two, and minus 0.05. And so these ones are the ones that contribute to this. And so if you want to see what those other values are, hopefully it's on this. I think it's not, they're a bit, the notes are a bit nasty looking. This was done a long, long time ago. But this is the basic matrix that we have. This is the matrix that we just drew or printed on the other thing, with 5 at the top left-hand side. We did the first 2 columns. They're written as to the exponent e, but these are the other ones that you can get. And so you can figure those out for yourselves. And so now what we have is a system of equations that we can solve. So we know that this is equal to 0. We know this is equal to 1. We know this is equal to 0, right? These are the boundary conditions. And we know that this is equal to 0 also. We know everything within this matrix. And so the only things that we don't know are these. And so we can solve for the values of these strengths. And if we do that, we come up with some values which I think are given here. These are the values of sink strengths. It's not set out very nicely, but the values are minus 1.06, minus 3.27. So this is minus 1.06, minus 3.27, and we have the other values as well, minus 1.06 and 0.35. This is 0.35, and this is also minus 1.06. And so physically, what these mean is these are the strengths of the injection that you have to have at each of these locations. And if you apply those, you automatically produce the right boundary conditions that we know. But we know the boundary conditions, so that's no real challenge to us. But what we would like to know is we'd like to know what the head is at this location, and the velocity at this location, and the head at this location, and the velocity at this location, the complementary conditions. So now what we can do is, if we go back to this, is we can write the complementary set of equations. So remember we made this point before, that the first part is we write the forward conditions like this. Now we know what all of these values are. So now what we could do is we could write a series of equations which now are the head at node 1, the velocity at node 2, the head at node 3, just in terms of geometry I'm bringing this down, and the velocity normal to the boundary at node 4 are equal to these equations again. But the complementary condition, right? It's going to be the sum of, this one is going to be the b values times mj. This is going to be equal to the sum of the a values, ij, mj. This is going to be the sum of the b values, done exactly the same way as before. but now we're getting the complementary conditions. And so just to take one, for instance, we take this value here. We want to calculate the, so what does that physically mean? So this value, this equation here is we're calculating the value of head at this point as a function of the known strength. So I suppose that would look something like, so worthwhile doing, it's going to be what? It's going to be the converse of this. So it's going to be the head at node 1 is equal to Aij, Mj, etc. And so it's going to be the heads from putting this on here. So it's going to be H1 is equal to oops. So we put the source on here. The self-influence of that source is H is equal to minus 0.27. So this is equal to minus 0.27 times M1 plus, we then put it on here. Its influence is minus 0.05. So it's minus 0.05 times M2. Just skip ahead this because we're running a bit out of time. The fourth one will be minus 0.05 times M4, just from symmetry, as you will see. And if we do this for this one, then the influence of 3 on 1 is plus 0.0062. So this is plus 0.0062 times M3. And if you wanted to, we could just do the last one, L, which, just to confirm, that this is the self-influence. And so now, actually, we don't have to do the whole suite of equations because we know that this value here is equal to this. We know that this value here is equal to this. And likewise, these two. And if we do that, we can calculate the value of head at node 1. If we want to get the velocity, then we do the same thing. We write the v dot n at 2, and we just write it as the sum of bij, mj. And so we know all of those. And so if you go back to these notes, again, not pretty notes, but maybe informative, I'm not sure. This now is this coefficient matrix, this second coefficient matrix here. So this is the first one in the forward solution to get the values of the sink strengths, which are here. And so now with these values of the sink strengths, we can get this complementary 4x4 matrix, which has similar problems. You see the numbers crop up again. And if we do that, we can solve for the values of the unknowns that we have. And so in other words, if we write out, actually the best place to do it is here, right? If we actually do this, I made this point here. So here we've solved for all these values of m. Now we can write this new set of equations. We've written the first one out, and we really only did the first one. But if we get this whole suite of equations, since we know the values of these m values, we know all the values inside the matrix, so we have complementary conditions here. And if you go through and look at the solutions, again, as I say, they're not pretty, but they are the solutions here. So these are the solutions. So this is equal to the head at node 1. This is the velocity at 2. This is the head at 3. And this is the velocity at 4. And if you draw those on to say exactly what they should be, then the head at this point is equal to 0.44. The head at this point is equal to, same, 0.44. The velocity across the boundary at this place is equal to minus 14.16, minus 14, and the velocity at the other point is equal to plus 9. And so I think this case is a case where it's 1 by 1. The upstream head is equal to 1, downstream head is equal to 0. And I think hydraulic conductivity in the equations is equal to 10. And so if you use Darcy's law to calculate V equals K dH dx, this is equal to 1, this is equal to 10. And so this should be equal to, these should be 10. It should be equal to minus 10 because the outward normal here is in this direction. So the dot product, V dot n, is equal to minus 10 across the boundary. It's going into it. And this should be equal to plus 10 again. It should be plus 10 coming out. And so it's a lousy, well, it's not a lousy solution. And of course, if you look at how this should change as you go from upstream to downstream, I do have to go to another class, is that this value here is going to be equal to exactly half of the head. So this should be 0.5. It's not. And so the reason it isn't is because it's really a coarse mesh. You know, you have one element on this side, you have one element on this side, and likewise. If you subdivided it so that instead of having just one element on each side, that you had, say, 4 elements on each side, like this, then you could solve it and you'd get a much better solution, except now you'd have, instead of solving 4 equations, which we've just done, you'd have 16, right? Because those would be the number of elements you'd have. And so it's not a bad solution, actually. 14 instead of 10, 9 instead of 10, and 0.44 instead of 0.5, just from doing this. But I think the main story, I guess, to come out of this is that it's called an indirect method because you solve in 2 parts. You solve indirectly. You distribute these sources around the boundary that replicate your boundary conditions. That tells you nothing, but it tells you the strength of the sources. And then once you have that, you can use that again in the subsequent procedure to figure out what the complementary conditions are in the boundaries. So it works for heads and velocities for flow problems. It works for forces or stresses and displacements for solid mechanics problems. And so that's just one exposition, if you like, of boundary element methods. We've gone over.